Alright, so next we're going to be discussing a vapor-liquid equilibrium flash calculation. But before we get into that, there's one more quantity that you're going to want to know besides Rayleigh law. So we're going to use Rayleigh's law again, but there's one other thing we want to know, which is this value, Ki. So Ki is just the ratio of mole fraction in the vapor phase to the mole fraction in the liquid phase. And looking at Rayleigh's law, we can rearrange this, solve for that, and we're going to have that this is equal to the pure component vapor pressure over the total pressure. So this is a useful value to know because this means that if we know the pressure of our system and we know the temperature, because temperature is used to calculate this pure component vapor pressure, then we can find this ratio of vapor to liquid phases, which is also known as Ki. So that's important to keep in mind. So as I said, we're going to be looking at a vapor-liquid equilibria flash calculation. Alright, so the premise of this calculation is that we're going to have a container. And this container is known as a flash drum. And in this container, we are going to have some sort of feed coming in. And we can label that feed with an F. So this F is going to be the amounts of moles of our mixture coming in. And so this will be known because we're the ones putting it in, so we know what we're putting in. And so we'll know, the amount and composition of that. And then within this flash drum, it's going to separate into a liquid and a vapor phase. So then there will usually be something up here that's taking out this vapor phase, and a pipe down here taking out the liquid phase. So, and these are represented by V and L respectively. So the V is the amount of moles of vapor that we end up with, and the L is the amount of liquid that we end up. So this is just a way to separate things. So, so we're going to know what feed is coming in, and we're also going to keep the pressure and the temperature of the system constant. So we're going to know those. And since we're going to know those, as I said before, we're going to know this ratio up here, Ki, which is ratio of moles in the vapor phase to moles in the liquid phase. So we're going to know that. And so the goal of our calculation, so we're going to want to calculate how many moles of vapor we've got. We're going to want to know what is the composition of this vapor. So, the mole fractions of each component in the vapor phase. We're going to want to calculate how much liquid we're going to get and the composition of this liquid. So that's a basic overview of what this vapor-liquid equilibrium flash calculation is going to look like. Alright, so the method we're going to look at today to solve one of these vapor-liquid equilibrium flash calculations is called the Rachford-Rice method. Alright, so this method was developed to solve one of these types of problems. So first thing we can look at is, so we have these three values, so F, V, and L. So moles of feed, moles of vapor, and moles of liquid. And, basic conservation of mass says that the moles in the feed are going to be equal to the moles that you get in the vapor plus the moles in the liquid. So that's the first equations we're going to look at. Also, for this you can do, so the moles, like you can do this for each component, so we can have the moles of the feed times Zi. So Zi is going to be, basically we don't know if it's in the gaseous phase or the liquid phase, so we don't want to write X or Y, so we're going to write Z. Because our feed could be all liquid, it could be all vapor, it could be a mixture of both, we don't really know. But this is going to be the mole fraction of component I in the feed. So this will just get us, multiplying that by the total moles in the feed is just going to get us the moles of component 1 that are in the feed. And similarly, then we'll go with moles in the vapor times mole fraction of component I in the vapor phase plus total moles in the liquid times mole fraction of component I in the vapor phase. So we can write this equation out for every component that we have, although it turns out it's not necessary to write it for every component. So for example, if you have a 2-component system, we can write, this for component 1, we can write it again for component 2, but then if you add those two things up, we're going to get back up to this equation. Similarly, if you were to have like a 3-component system, we could write it for component 1, write it for component 2, write it for component 3. If you added them all up, you're going to end up back at this equation. So what we need to do is we need to write this for one less component than we actually have. For a 3-component system, we only need to write this twice. For a 4-component system, we only need to write it 3 times, etc. So that's just important to keep in note because we don't need repetitive equations in here. So next thing we're going to want to remember is, I'll switch colors for this. So we're going to want to remember that the sum of all of the mole fractions in the vapor phase plus the sum of the mole fractions in the liquid phase, or oops, sorry, minus there, is going to be equal to 0, because sum of the mole fractions is always equal to 1, so it's just 1 minus 1 equal to 0. So that's pretty straightforward, but it will help us out with this problem. So we can also rewrite this, kind of combine the two summations, and these summations will be from component 1 to component n of component mole fraction in the vapor minus mole fraction in the liquid equals 0. Alright. So you'll notice we have 2 unknowns in this equation. That's not really helpful, so we're going to use this ki value that I described to you earlier and, kind of get rid of this y that we don't know so that everything's in terms of x. So to get this all in terms of x, we're going to want to solve this equation over here for yi and plug it in there. So rearranging this part right here, we'll get that yi, so mole fraction in the vapor phase is equal to this ratio ki times the mole fraction in the liquid phase. And we can plug that in over here, and we'll get the summation from 1 to n of ki times the mole fraction in liquid phase minus the mole fraction in the liquid phase is equal to 0. And then we can kind of factor that out and get that the summation from 1 to n of ki minus 1 times the mole fractions in the liquid phase is equal to 0. Alright, so next we're going to want to look at this equation over here, rearrange it a little bit. So first thing we're going to want to do is, again, like we did over here, get rid of this yi value. So we have F times the mole fraction going in is equal to the vapor, moles of vapor times Ki times mole fraction I. And then we can replace this L using this equation if we solve. So we'll have L equals F minus V. So moles in the liquid are equal to the moles in the feed minus the moles in the vapor. We can plug that in down here. So moles of the feed minus the moles of the vapor times this mole fraction in the liquid phase. And then you'll notice that both of these terms have that, so we can factor that out. And we'll have, so moles of feed times mole fraction in the feed is equal to mole fraction in the liquid times the vapor times Ki minus, or plus the feed minus the vapor. And then again, we can factor out the vapor within this parentheses. So we'll have moles of feed times the mole fraction of the feed equal to mole fraction in the liquid phase times moles of vapor times, oh, actually we can't do that, never mind. Because this is not one term in itself, F is a separate term from the vapor, so never mind about that. We cannot factor that more. But we can continue to solve for the mole fraction in the liquid phase, so by dividing this quantity out. So next we'll have the mole fraction in the liquid phase is equal to the moles of feed times the mole fraction in the feed over moles of vapor times Ki plus the feed minus the moles of vapor. Alright, so then we can take this and we can plug it in over here. So we'll get that summation from 1 to n is going to be equal to this, so the moles of the feed times the mole fraction of the feed over moles in the vapor times Ki plus moles in the feed minus moles in the vapor times Ki minus 1. That whole thing is going to be equal to 0. Alright, and then there is a little bit more that we can do to simplify this. So first, solve the summation, and we'll still have feed times Vi times Ki minus 1, and that will be over. So we're going to kind of factor just these two terms, but not the F. I think that's what I was trying to do a second ago, but anyway. So we're going to have vapor times Ki minus 1. So that's similar to that term up here. And then plus this moles in the feed is equal to 0. And then finally, we're going to divide the top and the bottom of this fraction here by F. So still the summation from 1 to n. So we'll divide this top by F, so we'll just have moles in the feed times Ki minus 1 over, so divide this term, so we'll have moles in the vapor over moles in the feed times Ki minus 1 plus moles in the feed over, or plus 1, but it's divided by the that's going to be equal to 0. So this, and is the equation that we're going to use for this Rachford-Rice method, because you'll notice, so we know the composition coming in, we know Ki because we know the pressure and the temperature. Well, 1 is a constant, and then again we know this Ki, we know 1, we know the feed, and so we're only solving for this vapor right here. And then the quantity vapor over moles in the vapor over the moles in the feed is just the fraction of the feed that becomes vapor. So the vapor fraction of the feed. And so that is what we're going to use to solve this kind of problem.